In this session, we will look at another important application of graphs in real life application. We already have seen weighted graphs. So, the application is again going to be useful when we are going to model our real life problems as weighted graph. So, weighted graphs are graphs in which edges carry some weight, or there is a numeric value associated to each edge, which we are going to call as weight. For example, in the flight route graph, the weight of an edge might represent the distance in miles or would indicate the time required. So, the weight of an edge would depend upon what application we want to solve on a given problem. So, typically the shortest path problem is defined as follows. We are given a weighted graph, directed or undirected, and we are given two vertices u and v, and we want to find a path of minimum total weight between u and v. We know that given any two vertices and if the graph is connected, there can be more than one path from u to v. Among these paths, we want to find one which is shortest. Shortest, we mean if you sum the weights of the edges which are on the path, that sum should be minimum, where length of a path is the sum of the weights of its edges. So, when we say minimum length would mean you look at the sum of the weight of the edges in the path and the sum of it. As clear from the definition of the problem, it has many applications in real life. It has applications in internet packet routing, where your graph is going to be a network and edges and their weights might be represented by the bandwidths available, or it could be driving directions where the distances becomes important, or flight reservations where you do not have a direct flight from source say x to destination y and you have to find a hopping flight. So, this particular notion of shortest path on a weighted graph has plenty of applications. As we see in the example below, if you are looking at a shortest path between Providence and Honolulu, which are marked by P, V, D and H, L, there are plenty of paths. One path could be you start from here, go here, here and here all the way. So, this is one path from the source to destination. The shortest path, as we mean in this case, is given by this path, correct. So, this also, like minimal spanning tree, is a problem of optimization problem. That means, we have numerous solutions to our problem. We want to find the one which has the least value. For each solution, we are going to have the numeric value associated to it, which is going to be the total weight of the path. So, given numerous paths from x to y, we want to find the one which is shortest or the smallest possible path. One way of looking at this problem is to look at the number of hops between 2 points, correct. For example, in this illustration, if you look at P, V, D and H and L, we can look at this path is the one which is taking the least number of hops, or it visits least number of vertices on its path, whereas any other path, correct, is going to visit more number of vertices on the path. So, the question is whether the shortest path that we are looking at is given by the minimum number of hops between the two vertices. It certainly is going to be at one solution of the problem. Question is whether it is always going to be the smallest path, smallest in terms of the total weight of the path. Now, if you consider your graph to be weighted graph, then it can be easily observed that minimum number of hop does not always mean a minimum distance. Now, the breadth first search on this particular graph would give us, given u and v, the minimum number of hops required to go from u to v. So, if the graph was not a weighted graph and we were trying to find the distances between two vertices or the number of hops between two vertices, the breadth first search would suit the purpose. Observe that the minimum number of hops does not always mean minimum distance. So, in the same example, if you are looking at source and destination, this is your source and x and say destination is y, we observe that there are plenty of paths which has 2 hops from x to y. If you look at this, one such path is this is path number 1, this is path number 2 and this is path number 3. So, we see that if we have the criteria as minimum number of hops in a weighted graph, then there can be many such paths, and in general it might happen that the one which has minimum number may not actually be the most efficient or the one which is least. In real life, such consideration do help us a lot in solving problems. For example, we might know that a certain route from x to y is short in distance, but goes through a heavy traffic. So, if my weight instead of distance would have been the time required to travel, then not necessarily the path which is shortest in distance would take the least time. So, in practice we do this quite often. If you know the path is going to go through heavy traffic, we try to avoid, maybe take a longer route which is going to take lesser time. So, in practice also we observe this many times. So, the weight and what it represents also is going to be important when we try to optimize our solutions, or we try to find a one which is going to be least. The algorithm that we are going to propose is going to be based on the greedy strategy, which is similar to minimal spanning tree. That means, we are trying to solve an optimization problem, and we solve this by doing what are called locally based decisions. So, we look at our current point and try to use that knowledge to take the best decision. So, initially when we start, we will assume that every city that you want to visit is infinitely far away. That is, you have no estimate to begin with of the source city. That is, every city will assume is at a large distance. Now, we perform something similar to breadth first search, optimistically guess that we have found the best path to each city as we encounter it. If we later discover we are wrong and find a better path, we update the distance to that city. So, we are going to use a greedy algorithm, and that would mean we would take decisions which are locally optimum decisions or locally based decisions. At some further instance, if you observe that the decisions were not correct, we update our decisions. So, as we said, we are going to mark initially every city to be far away from the source point. Like breadth first search, we are going to find all cities which are one hop away from our source, and we will check whether the mileage is less than what is currently marked for that city. And initially, we are going to mark all the cities at a distance infinity from the source. In the first step of algorithm, we visit all the cities or all the points which are adjacent to or which are one hop away from the source. We check the mileage or the weight of that edge with the already marked value for that vertex, and if necessary we update or we revise our guess, and we continue this for 2 hops and 3 hops, etc. We know that if our graph has n vertices and it is connected, then there is going to be a path of length n minus 1. So, the terminating condition will be when we have paths of length n minus 1. So, the first algorithm that we look at is called the Dijestra's algorithm. It computes the distances of all the vertices from a given start vertex x. So, instead of solving the problem of given source and given destination, we are in fact solving the problem given source to all destinations. So, this is called single source shortest path problem. So, we have a single source and we are solving a much general problem of a single source and destination. What we are solving is, given a single source and all possible destinations, we are going to compute the shortest path from this source vertex. The Dijestra's algorithm is going to be based on a few assumptions. Obviously, the graph has to be connected, that there should exist a path between a source and a destination. We will also assume that graph is undirected and simple, and crucially we will also assume that negative weight edges are not allowed, that is, edge weights are going to be all non-negative or bigger than or equal to 0. The second assumption, undirectedness can be dropped and can be extended even to a directed graph, whereas Dijestra's algorithm, non-negativity of edges cannot be dropped. We will see that the strategy that we are going to work out is crucially going to depend upon the fact that all the edges are having non-negative weights. So, the algorithm is going to grow a cloud of vertices beginning with the source vertex and eventually cover all the vertices. Initially, we are going to use function dv, which is going to represent the distance of v from S in the subgraph consisting of the cloud and the adjacent vertices. So, dv is going to give us the current estimate of the distance of v from source vertex. So, for every v, dv is going to be our current estimate of the length of the path from S to v, the length of the best path. Correct? So, we are going to talk always about a path which is going to be of least cost. So, at each step we add to the cloud a vertex u which is outside the cloud with the smallest label du. We update the labels of the vertices which are adjacent to u. Like minimal spanning tree, if you recollect, we added a vertex v with minimum label. Here also we are going to add a vertex u with minimum label which is outside the cloud, and once we do that, we are going to update the value of du for all the vertices which are going to be adjacent to u and are not in the cloud. This updation procedure is known as relaxation procedure. So, we are going to do a technique which is called an edge relaxation. So, in this particular edge relaxation procedure, we look at an edge which is say uz and use the vertex most recently added to the cloud. So, u, this is a vertex which is most recently added to the cloud, and as soon as u is going to be added to the cloud, we are going to look at all the vertices which are going to be adjacent to u. So, z is a vertex which is adjacent to u. We are going to update its d value. So, initially suppose d value was 75, that means the current estimate for z was, it is at a distance 75 from the source. Now, as soon as u has been added, we see that estimate for u is 50. The edge E has weight 10. So, we see that now the current estimate of D Z has been updated to 60. That means the estimate for as U is added to the cloud, we update our or we revise our estimate of length of the best path from S to Z. This technique is called edge relaxation technique. This, as we keep on adding elements to the cloud, all the adjacent vertices not in the cloud to these vertices, their d values are going to be updated. For example, later in somewhere in procedure we add something and something to the cloud to which Z is again adjacent, and the value of path via that node is less than 60, will update the value at Z at that particular instance. So, this edge relaxation strategy is going to help us update the current estimates of the edges or of the vertices who are adjacent to a node which has been recently added to the cloud. So, the discharge algorithm. So, initially we are going to say all vertices except the source are at a distance infinity. We are going to all put all the nodes in a priority queue using the distances as labels. So, the priority queue is going to be used as a structure for implementation discharge algorithm. Now, while the heap is not empty, we are going to remove the minimum element and perform, if needed, the edge relaxation. So, use of priority queue allows the finishing nodes to be found quickly in order log n time, where n is the number of vertices. It is easy to observe that running time of this algorithm is going to be m log n, where m is going to be number of edges and n is going to be the number of vertices. Let us try to see why discharge algorithm works. As we said, that algorithm is going to be based on adding edges or adding vertices to a cloud with some property. Now, why it works can be proved using the two properties, which are mainly a subpath of a shortest path is itself a shortest path, and very standard triangle inequality. We know that in triangle inequality, the distance between two vertices, that is distance between u and v, is going to be less than distance between u and x plus distance between x and v, where x is any other point on the graph. The triangle inequality is called so because this is similar to the triangle inequality that we have in standard Euclidean geometry. We also can easily show that your shortest path is actually a tree from start vertex to all other vertices. So, this property is put together allows us to prove that discharge algorithm precisely gives us a shortest path from a source to all destinations. Let us look at a illustration and try to see how the discharge algorithm is going to work. So, the discharge algorithm is going to have two parameters as an input, the graph and the vertex from where we are going to start our the vertex which is the source of your algorithm. Okay, so, the source vertex of the algorithm is known along with the graph. In this particular example, the source vertex is given by this. So, this is our source vertex. The d values are all mentioned inside. Now, the d values of the source is initialized to 0 and all other d values are initialized to infinity. This is the first set of discharge algorithm. Correct. Initially, when we start, all the vertices are at a infinite distance from the source. As we add now the source to our cloud, we will update all the labels for the adjacent vertices. So, now we see that this is 1, 2 and 3, these vertices are adjacent to the source vertex, or these are the vertices which are at a single hop or at a distance 1 from the source vertex. We look at their d values. Recollect, for this the d values initially were all infinite. Okay. So, this were all infinite. So, as soon as we add this to the cloud, we will update this d values which were infinite. In this case, these are going to be updated, since infinite is bigger than any other any other integer. These are going to be updated to the weights of the edges which are going to connect these vertices. And now we continue. So, we now have, so now we are going to add, next we pick up the node whose d label is going to be least, which is here. Of all the vertices, now the d label of this vertex is least. Now, we look at all the vertices which are adjacent to these vertices and update its d values. So, the d values we see these vertices are all adjacent to these vertices, to the yellow vertex JFK. So, we update now their d values. Recollect, this the d value for this in the last iteration or was infinite. So, as soon as this node gets added to the cloud, the d value of this becomes 184 plus 187, which is 371, which is less than infinite. Similarly, this was infinite before this was added to the cloud. Now, as soon as this is added to the cloud, its d value is updated to 184 plus 144, and similarly for this vertex. Now, d value of this is already bigger than 184, sorry, the d value of this is less than 184 plus 740. So, this is not updated. We know that 621 is less than 740 plus 184. Since this is there, the d value at this particular node is not updated. And now, we continue with this procedure. Now, we look at the next node with the least d value. In this case, that is going to be 328. So, we add that now to our cloud. So, next 320 is added to the cloud. So, we have done, now we are at a nodes which are at a distance 2 from our initial, correct. This was the source vertex and this vertex is at a distance 2. In this case, distance is the number of hops that we are looking at. Now, we continue with this. Now, we see that the only vertex to which this is adjacent is JFK itself, which already we know is this, and the length of this edge is 849. So, this still remains less than this, the length of this path. So, we do not update anything else, we simply add this to our path. Next, we pick up a node whose d value is least, which is this. So, the next node that we are going to add to our cloud is going to be the one whose d value is 371. And now, we continue our procedure. As soon as we add this, we see that this is adjacent to this. So, we update at this up to certain this stage, its d value is infinite. So, it has been updated now. As so, we know the d estimate for this is 371, that is length of the least path from this to this is going to have length 371. So, the estimate for this is going to be 371 plus 2704, which is precisely this. Similarly, we are going to update all the d values. Next, we choose vertex with the least d value, in this case which is this. So, we are going to add this to our cloud. Now, if you look at In this case, in the earlier case, before this was added, its value is 1575. Now, as soon as this is added, we see that the D value, which in earlier before this was added to the cloud, was 1575. Now, we see that if you look at the path up to here, we know its D value is 621. So, the D value for this is going to be 621 plus 802, which is 1423. We know 1423 is less than 1575. So, we update the estimate of the path from BWI to DFW by 1423. So, we continue doing this until we add. So, next is going to be the one which is going to have 946, and at this certain stage we have found, we have added all the vertices to our cloud, and we have also, so this was our source. So, we have found the shortest distances and also the path from given source S to all possible destinations. The D values here indicate the shortest path and the length of the shortest path from S to that particular node. Now, it is easy to see that discharge algorithm does not work when we have negative weight edges. Now, discharge algorithm we have seen is based on adding vertices by increasing distances. Now, if a node with negative incident edge were to be added late to a cloud, it could create problem for the estimates of the vertices which are already in the cloud. Now, suppose you look at this example where you have negative weights and we are using discharge algorithm. Now, if you look at the case when F is added to the cloud. Now, when we have this, the distance up to this particular state is 5. So, the D estimate for C is 5 as D was added to the cloud. As soon as D gets added to the cloud, in discharge algorithm, the D value of C is going to be 5. Now, when F gets added to the cloud, then we see that C's distance is 1, but it is already in the cloud with DC equal to 5. So, we cannot update that, correct. So, what does that mean is, if you add a node, if you add a node with a negative incident edge, then it could create problem for the distance of the vertices which are already in the cloud. So, C's true distance is 1, but since it is already in the cloud, its distance is already 5. We cannot update, right? So, since C is already in the cloud, we cannot update the estimate for C. We have already C is in the cloud would mean we already know the shortest or the length of the shortest distance between A and C. So, we see that discharge algorithm does not work when you have negative weight edges. So, we look at another algorithm which is called Bellman-Ford algorithm. It works even when we have negative weight edges. It assumes that we have directed edges. It does not work if you have undirected edges. Because if you work with undirected edges, then the negative edge would also give us a negative weight cycle, and that means every time we traverse this negative weight cycle, the distance estimate is going to grow lesser and lesser, correct. That what we are trying to say is, suppose we have a vertex u and a vertex v and in the path from u to v we have a negative weight cycle. So, this is a cycle and it has negative weight. This would move on. Every time we traverse this cycle, our weight is going to decrease by a factor of the length of the cycle. So, we would never be able to find the minimum the least distance between u and v. So, for Bellman-Ford algorithm, we need directed edges or we need a directed graph in which negative weight edges are allowed. The Bellman-Ford algorithm computes the shortest length of the shortest path if there are no negative weight cycles, and it can be extended also to detect a negative weight cycle. That means, the Bellman-Ford algorithm will return either the shortest distance between the source and the destination, or will say that there is a negative weight cycle in the graph. In this algorithm, in ith iteration, we find all shortest paths that use I edges. So, unlike Bellman-Ford algorithm, it uses edge relaxation, but not in conjunction with the greedy method. If you recollect, when we did edge relaxation, we used greedy method to go choose the next vertex. The next vertex was chosen such that the d value was the least. So, in Bellman-Ford algorithm, for each I, so again we are going to start with the source vertex. We also going to use d values, which are going to be first initialized to infinity other than the source vertex. Now, for every I which is from 1 to n minus 1 or v minus 1, and for every outgoing edge we are going to do the relaxation. So, for I equal to 1, we are going to look at all the edges of length 1 going out from u and do the relaxation for them. If there are no more edges left for relaxation, we return the label DUs, which gives the shortest length of the shortest from S to U. Now, if you look at the following example, Bellman-Ford example. So, this is the source vertex. Now, initially all the vertices other than the source vertex, their d values have been initialized to infinity. The d value of S is initialized to 0. So, initially all the vertices are at an infinite distance from the source vertex. Now, we initialize all the edges which are of length 1 and going out from S. So, we look at these edges which are going out of S, update their d values. Again, this is the same edge relaxation technique. So, we update these values to 6 and 7 and now continue. Now, we try to look at all vertices which are of length 2, which are at a distance 2 from the source. So, we know these are precisely. So, for every vertex here we have this edge which is going out of this and this edge which is going out of this, and we also have this edge going out of this vertex. But as we see that so this is going to go here. So, we are trying to update d values for all vertices which are now at a distance 2 from the source. In this case, we see that if you look at this this path, this is d value 6, this is minus 4. So, if you traverse this d value becomes 2. If you traverse this, d value is 16. So, we update this to 2. Whereas, if you look at this vertex and its d value, if you traverse through this 6 and this is going to be 5, so its d value is 11. Whereas, if I look at the alternative path which is from here, d value is 7 and this edge its value is minus 3. So, this is going to be 4. So, the d value of this is going to be updated to 4 and not to 11. So, you can see that this is updated to 4 and this is updated to 2. So, what we have done is we have looked at all the edges which are going out from these two vertex, which has been added in the earlier step, or which has already been, or their distances has already been computed. Using this, we update the distances of this vertices which are at distance 2 from the source vertex. And now we look at the other vertices. Now we look at this vertices which has been, so this is a vertex which has been added to our, and so we look at now these are the vertices which are at distance 2. Look at all the edges which are going to go out of this vertices. Now this vertex we have, it goes out here, the weight for this was 4 and this is minus 2. So, this has been updated to 2. This is 2 and if this is 8. So, this does not get updated, only this is updated at this particular step. Now, we look at this vertex and try to find the edges which are going out of that vertex. So, that is precisely only this one which is left. So, this estimate, if you look at the earlier estimate this for this was 2. Now, if you come here, this is minus 4, and so if I go a path like this weight is 2, this is minus 4. So, this becomes minus 2. So, at this stage the Bellman-Ford is going to terminate and return all the d values of the nodes. It is easy to check that this algorithm is going to run in time VE, which is nothing but OMN. So, you see that Dijestra's algorithm runs faster than Bellman-Ford algorithm, but it works in restrictive cases. That means, only in the cases when we do not have negative weights, or we have only weights which are non-negative. So, only for those graphs Dijestra's algorithm works, whereas Bellman-Ford algorithm works even if you have negative weights. The Bellman-Ford algorithm returns either if there is a negative weight cycle, it returns that, or it returns the shortest path between given source and any destination. Thank you.